So with our binomial distributions, we were looking at discrete data. 50 trials, certain amount being successful, a certain amount being a failure. When you start to look at bigger and bigger data, you're looking at continuous data, and all of a sudden you can't just say just one value. You're looking at the whole thing and all possibilities. So for example, if you were looking at heights, it's not like we grow 1 inch at a time. That would be very entertaining to watch. Someone they're 5'1", the next day, at 2 o'clock, they become 5'2", and you just watch this person go blip, and they bounce up a whole inch. That would be fascinating to watch. We measure our heights by the inch, but we don't actually grow by the inch. We grow continuously. Same thing with our shoe sizes. We measure our shoe sizes in discrete numbers, size 10, 10 and a half, 11, but it's not like your feet all of a sudden are like on the verge, and all of a sudden, boom, they bump forward. So we have continuous data, and we still have an average, and what we find is that our average is right in the middle of this bell curve. And some people are above average, and some people are below average. Most people are around the average, and as you get farther from the average, the more rare it is. You think about heights. There's average heights. There are some people that are quite a bit taller and quite a bit shorter, but the majority are around an average. So our normal distribution is defined by two things. One is the mean, and the mean will always appear right in the middle of your normal distribution. And the variance, which is just the standard deviation squared, the variance is telling you how wide or how narrow all of your data is. And what the normal distribution shows is the same thing that our probability distribution chart showed. So for example, if we flipped a coin 3 times, here's my normal distribution chart. Three times, did I say? You could get 0 heads, 1 head, 2 heads. 3 heads, we figured out that this was 1/8, 3/8, 3/8, 1/8. Those were our probabilities. If we drew a graph to show these probabilities, and I put my scores here, 0 to 1, 1 to 2, 2 to 3, 3 to 4, and I put my probability up here, so I'm going up to 3/8, so I'm going to put 1/2 here, or 4/8. From 0 to 1, the probability is 1/8. To get a 1, the probability was 3/8, 3/8, 1/8. And it has the same kind of idea as a normal curve. If we did 50 trials of our flipping our coin, the 25 would still be the highest one, and everything else would be less likely as you go away. And it would get closer. You would have a histogram that would be similar to this, but it would be closer to the normal curve. And so once you're dealing with an infinite amount of data, then it really becomes super close to the curve. Now, some things that are important and some things for how the normal distribution relates to probability, we know in our probability distribution chart that this adds up to 1. So when we're looking at these bars, all 4 of those bars in that histogram add up to 1. The same thing with the normal distribution. Whatever you get as your curve, the area, I love this unit because I get to color things in with crayon. Here we go. Oh, let's do purple. This area, should have been an artist. So this area inside that curve will always be 1. And we're going to find out that finding the area under that curve is going to be equal to the probability of something happening. So it's defined by our mean. The n here stands for normal distribution, mean, and our variance. And the way that our variance shows up is the square root of our variance. That's the symbol for standard deviation. And most data is spread 3 standard deviations above and 3 standard deviations below. So we've got a bunch of important data here. Okay? We already talked about, and if you like to highlight things, the total area under that curve is 1. Some other interesting things happen is when you look at your standard deviations, and we talked a little bit about this before, and you go up 1 standard deviation and down 1 standard deviation, approximately 68% of your data will fall in there. So if we find out what is the average height of Canadians, and we find out what the standard deviation is, so if we find out that the average height of Canadians is 5'6", and standard deviation is 4 inches, we would be able to say that 68% of Canadians are between 5'2" and 5'10". I'm not sure if my data seems right, but that's how that data would read. And as soon as you go 2 standard deviations, so we have our mean here, and we move up standard deviations this way and down standard deviations this way. As soon as you go 2 standard deviations away from the mean, that would be roughly 95% of the data. And only 5% would be outside of that. So if I take my example, and now we can decide, do we think this is true or not? And I said 5'6" was the average height of Canadians, and 4 inches was my standard deviation. So if I go up 4 twice, that will get to 6'2". And if I go down 4 twice, that will get to 4'10". 95% of Canadians, according to that data, should be between 4'10" and 6'2", and only 5% higher than that. Does that seem reasonable? You might start to wonder. You think, well, maybe there's a little bit more that are taller than that, and maybe 4'10", if we're talking adults, maybe that would be a little bit low for Canadians, but I'm not sure. So we would think about that. But that's what that data would mean. And as soon as you go 3 standard deviations above the mean, it's almost 100%. It's very rare to have things outside of that. So we get something that's sometimes called the 68-95-99.7 rule, which stands for 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. Those are estimates. If we look at our data here, it's not actually 68, it's 68.2. And if we add the 13.6 on other sides, it's actually 95.4. And it might be 99.7 something. But those are our estimates. And it's just to give you an idea for the percentages. So if you have a mean and a standard deviation, you get a really good picture for what things are like. For example, I can take 2 different populations. I can study a grade 7 or a grade 8 class, weigh all the kids, and find out that the average weight is 105 pounds. But if we look at a grade 7 or 8 class, if you think back to when you were in grade 7 and 8, there were some big kids already, weren't there? There's some really big kids in 7 and 8. And there were some kids that hadn't even thought to start to grow yet in grade 7 or 8, like super small. So there's a big range. So even though the average weight was, what did I say, 105 pounds, your standard deviation might be big because there might be a wide spread. There might be that grade 7 or 8 kid that's already 210 pounds, and there might be that grade 7 or 8 kid that still needs to have a booster seat and sit in the back of the van because they're only 55 pounds. Okay? It can happen. That being said, I could take another population and get that same average. I go down to the horse races at Assiniboine Downs, I get all the jockeys, I weigh them, and the average weight is 105 pounds. But what could you expect about the standard deviation? You're not going to get that 200-pound jockey. That's not going to be their line of work, right? So you're going to measure and you're going to find out that your standard deviation is really small because most of the jockeys are all the same size, even though they have a light weight of 105 pounds. In that case, your standard deviation is going to be small. So we have a normal curve. The middle is always our mean value, and our sigma stands for standard deviations. We're going to be looking at putting actual data under there for these little yellow dots. So if we find out that 105 was our mean and 7 pounds was our standard deviation, then we'd write 105, 112, 119, 126. Okay? We'll also be looking at something called the standard normal distribution, which instead of writing our mean as whatever it is, like 105, we will write the mean at 0. And then instead of counting up by sevens, we'll just count up by standard deviations. So what that allows us to do is that allows us to create a score that can compare people. And we can say that your standard deviation, if I measure your height compared to the average, maybe your score would be a 1.5. And a 1.5 score would mean that you are 1.5 standard deviations above the mean. So it's a way of just talking about spread of data just by the standard deviations. And we got fancy symbol, woohoo, phi, for the standard normal distribution. So here is your standard normal curve. When you make your average 0 and you just count by standard deviations. So again, you can see that once you get to 3 standard deviations above or below, you have counted almost all of the data. And we call any score that you get on here a z-score. And that z-score is telling you how many standard deviations above or below the average you are. So if your z-score is -1, you are 1 standard deviation below the mean. This next little part isn't in your notes, and you won't have to know this, but it's just for interest's sake. If you wanted to find an equation for that curve, you can look it up, but it's quite simple. Just happens to have e and pi and square roots and powers in it. Whoa. So if you were to graph whatever your standard deviation is, whatever your mean is, so wherever you see those values, you'd plug in your mean and your standard deviation. If you were to graph this, you would get a perfect bell curve. And we'll show you how you can do that quick and simple in your calculator during this lesson. The mean, the median, and the mode for a normal distribution are all the same. They're right in the middle. And everything is symmetrical in a normal distribution. Notation-wise, so we write a z-score normal distribution. N stands for normal distribution. Again, the 0 is your mean, and the 1 is your variance, or your standard deviation squared. And we're going to be able to find these things and calculate these values with something called normal CDF. There are 4 things that you put into there. The last two you can leave out. In fact, I think with your newer calculators it works out really nice. They default to 0 and 1. So we're going to look at what this looks like, and what it does is it calculates the area. So this is best seen by looking at an example. So here we have data that's been taken, and an average has been found, and a standard deviation has been found. So 18-year-old males have a mean of 95 centimeters and a standard deviation of 8 centimeters for chest measurements. So the first thing that we can do is draw a normal curve, put our mean in the middle, count 3 standard deviations above. So we're going to go by 8s, 95, 103, 111, 119. And 3 standard deviations below, down to 87, down to 79, down to 71. And then our first question says, what are the chances if you randomly picked someone who was 18, what are the chances that they would have a chest measurement size between 87 and 103? Well, that shows up if we draw a line where 87 is, and we draw a line where 103 is. Take out our crayons. Yes. I'm going to go with that color. Oh, nice. It looks so much like a crayon, doesn't it? Or do you guys even remember coloring with crayons? And if you use your imagination just right, you can actually smell the wax when you use that smartboard pen. Okay. So if we were to estimate this, we have our 68, 95, 99.7 rule. If we were to estimate this, that lined up perfectly. It lined up perfectly 1 standard deviation below, 1 standard deviation above. We would estimate this is going to be approximately 68%. If we want to figure this out exactly, we're going to go to our calculator. And the same place that we found binomial PDF and binom CDF, we're going to use normal CDF. And the normal CDF function will say, what is your lower score, what is your upper score, what is your average, or what is your mean, and what is your standard deviation. So for our question right here, we're wanting to find between 87 and 103. So our lower score is 87, our upper score is 103. Our average was 95, and our standard deviation was 8. So again, if you have a newer operating system, this is how it shows up. If you have an older operating system, you just get normal CDF, and then you have to know that you put in your lower score, upper score, mean, and then standard deviation. Once we push enter on this, we said it was 68%. To 3 significant figures, it would be 0.683. So this is our score. If you don't have that newer one, you have to know that you have to put in the lower, the upper, the mean, and the standard deviation. If you would like to see this on your graphing calculator, first of all, you'd have to go to your window and set your window up to match. So looking at my data here, it looks like I go from 71 to 119. That would be 3 3 standard deviations above and below my mean. Since my standard deviation, do you know what that XSCL stands for? That is how the scale on your x-axis is split up. I'm just going to put 8 because that's what our standard deviation is. I don't know if it'll match up nicely or not. Your probability, the whole area has to equal 1. So your probabilities aren't going to go very high up. Nothing's going to be a really high percentage. I'm going to just guess at 0.5 to start with. We'll see what our graph looks like, and we might have to adjust our window after that. Okay. So I tried to set up my x and my y for this normal distribution. Two ways we can go about graphing it. One, if you go back to second distribution, where it had normal CDF and everything. If you go over to draw, the first one says shade norm. If you push enter on shade norm, it says what do you want for your lower, what do you want for your upper? 87, 103, try that again, 103, my mean was 95, my standard deviation was 8. Fun part, what color do we want? Okay. Ooh. Wow. Does anybody see a color that really looks like calling them right now? Medium gray? Okay. Awesome. I mean, it's math class. It can't be too bright and exciting, right? Okay. So now that when we draw this, ooh, there's our medium gray. It draws things out. We chose 0.5 as our height. If we want more, like, can you see that if I would go 0.1 as my height, it would draw it a little bit better. So I'm going to just change it to 0.1. Now when I hit enter, and if I go back to graph, nothing shows up. You have to go back and do that shade norm again, or you can just highlight it again and push enter and it'll draw it again. So that's exactly what we drew. This function isn't going to be that useful for you because you're going to use normal CDF way more often, and you're going to draw your own picture, and it's going to be quicker to draw your own picture and do normal CDF than to do this. But you can see that it also calculates the area for you this way. Okay. So you get that little graph if you use shade norm. What is the probability that an 18-year-old male has a chest size less than 87? So once again, you take your graph and you draw it again. There we go. Perfect. And this time we're looking for less than 87. I'm sorry that I didn't pre-warn you that it would have been helpful to bring crayons to class. So now when we go to our normal CDF to calculate this, when you went to it the first time, you might have noticed that the lower value had a 1 and then an e to the negative 99. Or was it negative 1 e to the, it was negative 1 e to the 99. That sounds better. Negative 1 e, and it's to the positive 99, right? What that is, that e to the 99 is like scientific notation. That means 10 to the power 99. In other words, you'd have 99 zeros there. How big of a negative number is that? That's huge. The idea is that your normal distribution? This curve goes on forever. In theory, you could get someone with a chest size, because this goes on forever, of 2 kilometers. In theory. Okay? Now, what happens to the normal distribution is there's like an asymptote there that it gets so close to 0 that your probabilities are so tiny that they never happen. They're basically, as soon as you go 5 standard deviations away from the mean, your probability is basically already 0. But in theory, it goes on forever. And did that just knock? Okay. Hello. Okay. So in theory, it could go on forever. But we all know that a 2 kilometer chest size is like, yeah, that's not even Incredible Hulk material for the movies, right? But in theory, it could happen. So when we set our lower at -1, I don't know how to say that number if it had 99 zeros. Big. -1 big. And now we want to go as an upper number up to 87. Our mean is still 95. And our standard deviation is still 8. We paste it in there. And we've got a 0.159% chance. What is the probability that has a chest size greater? Well, if we draw that in, seriously, if you have time, sometime to come in and just color with the crayon on the smartboard, there's some innate joy that just comes from doing that. So I'd like to share that experience with you. So if you want to come in sometime, we can pull up coloring pages from the internet and crayon it on the smartboard. That's right. I have to put that in as a course. That is optional course, right? Instead of taking Juilliard, maybe you want to take coloring with Mr. JR. I don't know if it would get approved by the province. We'd have to come up with some sort of creative name. Postmodern art, there we go. Something like that. So you could use your normal CDF for this one and start at your lower value at 87 and your upper value of the 1 e to the 99 to make it something huge. Or, since we figured out that it was 15.9% chance for less than 87, and the whole area is going to be 1, or 100%, then it's going to be 1 minus 0.159, or 84.1, as your probability of it being bigger than 87. Yeah, that is an 8. This one right here?
Yeah, it looked like an E.
Yeah, it's a weird, there we go. Oh my goodness. All right, beautiful. Another course, making 8s with Mr. JR. So I'd like you to try the next two try drawing the picture with your normal curve with 3 standard deviations above and below. Shading in, we should make a new verb, or crayoning the right area, and then using normal CDF to calculate the probability. There's your picture. You can see how you're doing, and if you want to see if you got the same values, do before the bell rings. So there you go for the next one. That would be the diagram, and then if you use normal CDF, that's what you would get.